In this video lecture, we will see members subjected to shear stress. Consider a rectangular section ABCD of uniform cross-sectional area and unit thickness as shown in this figure. Section subjected to shear stress throughout and face AB and CD. On this face AB and CD, shear stress subjected tau, and the faces BC and AD is subjected equal and opposite shear stress tau. This is BC and this is AD, equal and opposite shear stress tau. Consider a plane BE inclined at an angle theta to face BC. This is BC face and this BE face is inclined at an angle theta to this BC. Vertical force on BC is equal to shear stress multiplied by area of BC. Vertical force on this BC plane is equal to shear stress multiplied by area of BC. Shear stress is tau and area of BC is BC into 1. So tau BC is vertical force on BC. Now vertical stress on BE. Vertical stress on this BE is vertical force on BC upon area of plane BE. Vertical force on BC is this tau BC into 1. This tau BC into 1 upon area of plane BE is BE into 1. So, and this is theta. So, see, cos theta is equal to adjacent side upon hypotenuse. Adjacent side is this BC and hypotenuse is BE. So this BC upon BE is cos theta and this tau as it is. So vertical stress on BE is equal to tau cos theta. Now horizontal force on CE. On this space CE, horizontal force is shear stress multiplied by area of CE. Shear stress denoted as tau and area of CE is CE into 1. So tau CE is horizontal force on CE. C force is equal to stress into area. Horizontal force on this CE plane is equal to shear stress multiplied by area of CE, and stress is equal to force upon area. Horizontal force on this BC inclined plane is horizontal force on CE upon area of plane B. Horizontal force on CE is tau CE into 1, tau CE into 1 upon B is area of plane. Therefore, tau sin theta. CE upon BE is sin theta. Sin theta is equal to opposite side CE upon hypotenuse is BE. Now consider this plane BE. Plane BE. This is tau sin theta and this is tau cos theta. See, this is tau sin theta, horizontal stress on BE, and tau cos theta, vertical stress on BE. So tau sin theta is horizontal stress on inclined plane BE and tau cos theta is vertical stress on inclined plane BE. And this is normal force sigma n1, sigma n2. And this is tangential sigma t1 and sigma t2. Normal stress, not force, normal stress sigma n1, normal stress sigma n2, tangential stress sigma n1, tangential stress sigma t2. This is x-axis and this is y-axis. So resultant normal stress is equal to sigma n is equal to sigma n1 plus sigma n2. Here sigma n is equal to this sigma n1 sigma n1 plus sigma n2, and sigma n1 is nothing but the tau sin theta into cos theta. See, this is tau sin theta. That means resolve this tau sin theta. See, resolve this tau sin theta into y-axis. This theta is near to this tau sin theta, so tau sin theta into cos of theta. So this term is tau sin theta into cos of theta, and sigma n2 is this sigma n2. Sigma n2 also resolve here. This is tau cos theta, and theta is here, so tau cos theta into sin theta. So this is tau cos theta into sin theta. This tau cos theta resolved into y-axis, and this tau sin theta resolved into y-axis, and this is sigma n1 plus sigma n2. Now this tau take common, that means 2 tau and sin theta into cos theta remaining. So 2 tau sin theta into cos theta, tau as it is 2 sin theta into cos theta is sin 2 theta. Therefore, stress in normal stress is, resultant normal stress is tau sin 2 theta. Now next is resultant tangential stress. Tangential stress acts on this x-axis, sigma t1 and sigma t2, and see this sigma t1 is positive x-axis and sigma t2 is negative x-axis. They both acting different directions. So this tau cos theta resolve it here on x-axis. That means tau cos theta into theta is near to this axis, that means cos theta, tau cos theta into cos theta. And this is this, and this is minus sign because this acts, this is not acting on x-axis towards x-axis, this is acting on negative x-axis. See, this x-axis is like this, and this is acting on here, this side. And this tau sin theta is resolved like this, tau sin theta into theta is not near to this tau sin theta axis, so tau sin theta into sin theta. So this is tau sin theta into tau sin theta. Now tau sin square theta minus tau cos square theta, minus tau take common, cos square theta minus sin square theta is cos 2 theta. So tangential stress is minus tau cos 2 theta. Next is resultant stress. We all know that resultant stress is nothing but the resultant of the normal stress, and the tangential stress is called as resultant stress. This is normal stress and this is tangential stress, and this is resultant stress. Resultant of this normal stress and tangential stress is this resultant stress, and it is denoted by sigma r is equal to square root of sigma n square plus sigma t square. And next is angle of obliquity. Angle of obliquity is the angle made by the resultant stress with the normal stress, and it is denoted by phi. Angle made by this resultant stress and normal stress denoted as phi, and is equal to tan inverse of stress, tangential stress upon normal stress. Now the tangential stress sigma t is maximum when sine 2 theta is maximum, and the maximum value of sine 2 theta is C. First, the principal planes and stresses. Shear stress should be zero on principal plane. This sigma t is equal to minus t cos 2 theta. See, this sigma t is equal to minus tau cos 2 theta, and this 2 theta is equal to 90 degree or 270 degree. Consider this 2 theta is equal to 90 degree or 270 degree. That means theta is equal to 90 upon 2 is 45 degree, or 270 upon 2 is 135 degree. So cos of 90 is 0, and cos of 135 is, that means cos of 270 is also 0. So this sigma t is equal to tangential stress is equal to 0 when theta is equal to 45 degree or 135 degree. Thus the plane inclined at 45 degree and 135 degree with BC, this BC, carry no shear stress, and hence they are principal planes. Shear stress should be 0 on principal plane. When theta is equal to 45 degree or 135 degree, tangential stress is equal to 0. Now principal stress this sigma n is equal to tau sine 2 theta. When theta is equal to 45 degree, sigma n is equal to tau, and when theta is equal to 135 degree, sigma n is equal to minus tau. That means the major principal stress is tau tensile, and minor principal stress is tau compressive. This positive sign, that means tensile, and negative, that means compressive. At theta is equal to 45 degree, normal stress is tensile tau, and at theta is equal to 135 degree, normal stress is compressive tau. So this is derivation of member subjected to shear stress. Resultant normal stress is tau sine 2 theta. Resultant tangential stress is minus tau cos 2 theta. Resultant stress is sigma r is equal to square root of sigma n square plus sigma t square, and angle of obliquity phi is equal to tan inverse of tangential stress upon normal stress. And principal plane theta is equal to 45 degree and theta is equal to 135 degree, tangential stress is 0, and normal stress is at theta is equal to 45 degree tensile tau, and at theta is equal to 135 degree compressive tau. Thank you very much.